My name is Danielle, and I will be your MC for today's event. First,
Apologies, if you give us a minute, I think our MC has just lost a connection. Should be right back.
hi, sorry, I was having some technical difficulties, but can everyone hear me now?
Yes, all good, Danielle. Thanks.
Okay, sorry, it just quit. Okay, sorry, I'll start off. On behalf of WS Education, I just want to thank everyone for joining us today. There are a few things to note before we kickstart the workshop. This event will include a Q&A segment at the end, so please feel free to submit questions into the chat at any time during the webinar. And also note that this webinar is being recorded and the recording will be shared publicly online after the event. So now I will talk about the book series. If you don't already know, I'm a Math Star is a book series published by WS Education. The series comprises challenging math puzzles, which are presented and solved step by step in story form. Set one of the series comprises 3 books, as you can see on the slide. Our speakers for today are Prof. Tae Nguyen and Dr. Yip Ban Ha. Our first speaker is Prof. Tae Nguyen, an associate professor in the National Institute of Education. Prof. Tae represents Dr. Boaz, a group of educators who love children, math, and problem solving, and who are also the named author of the I'm a Math Star series. Dr. Yip is one of the world's leading experts in professional development for teachers in Singapore mathematics. An accomplished and inspirational speaker, Dr. Yip spent 10 years at NIE, where he taught a range of educational courses and was involved in several funded research programs in mathematical education. He continues to teach courses and supervise practicums at tertiary institutions around the world. He sits on the advisory board of several schools in Singapore and Asia, and was also a consultant for World Bank projects. Now I will hand over the time to Prof. Tae to start.
Hello, everyone. Can you see my slides?
Yes, Prof. Quite good.
Okay. Welcome to this talk. Thanks, Daniel, for the introduction. Today's talk is on mathematical problem solving for kids, and the emphasis is on strategies and heuristics. I hope that in this talk, I will be able to explain how we use stories to bring a child through the process of mathematical problem solving. We also hope to give some tips to get children or those who are young at heart to understand maths problems better. One of the key things is to break a maths problem into simpler parts or simpler terms. And the approach we're going to use is a story approach. Since I was young, I've always been interested in stories. In particular, I'm interested in detective stories. And this is my hero, Hercule Poirot. There is a whole box set of all of Poirot's stories. I got the Christie stories on Hercule Poirot, and I bought all of them in this box set. Now, what makes a detective story interesting is not that the murder is committed and the police catches the murderer the next day. We are interested to know how the detective figured out the murderer, and also we are interested to know how the detective thinks. As Poirot would say, how the little gray cells, how do they think? Today, to illustrate these thinking processes, I will bring you through a maths problem. We've already written 3 books with 3 different maths problems. Today, I will have a new one. This is the problem. Or if you want to think about it, this is the thing that Poirot would encounter. How is he going to solve it? Let me read through the problem. A group of 10 children are in an escape room. The gatekeeper sets the following challenge. The 10 children are to be placed on a flight of 10 steps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. With everyone facing downwards. A hat, either red or blue in color, is placed on each child's head. The hat on each child is visible to all the children above him or her. In other words, this person can see all this. You can see red, blue, red, blue, red, 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 blue, blue. This person can see blue, red, blue, but of course, this person can't see the color of his own hat, neither can he see the color of the person above. Each child, starting from the one at the very top, this one, is to guess the color of his or her hat by shouting out either red or blue. All the children will be released from the escape room if at most one child gets a wrong guess. In other words, if there were 10 of them here, at least 9 must get it correct. So it's either 9 correct or 10 correct. If 8 correct, then they are stuck in that escape room. Now, before the hats are placed on the children and before the children line up on the steps, they are allowed to discuss a strategy. What strategy will work? Now, why don't you put on your thinking hats? How would you solve this problem? I've already given you the problem, maybe that enticed you to attend this talk. But I'll give you a minute to think about the problem. So I will go back to the previous slide to let you have a look at the problem. And you will think, how am I going to solve this problem? If I were one of these 10 kids, what strategy would we all agree on? maybe we should simply guess. Yeah? So the first guy guessed red. Oh God, good, he's got it correct. This guy guessed red. Oh, 2 persons got it correct. Now what's the chance this guy will guess correct? And then this is correct, this is correct. And everybody is correct. If you've done some probability, then the probability is half times half times half times half times half. It gets worse and worse. Well, what do we do? How do we solve this problem? In mathematics, we have a general strategy or general strategies for attacking problems. This is our experience as professional mathematicians. That's my job as well, to solve rather tough problems in which I have to write papers and get them published. But whether I'm doing this very tough problem or when I was doing my undergraduate problem solving, we do use general strategies. They are called heuristics. Heuristic is the Greek word akin to the word eureka, which means to discover. So it's a general strategy to discover something. What are we trying to discover? We're trying to discover not immediately the solution, but something more about the problem, something possibly to make an impact. Just like Poirot, the detective, tries to solve a problem, he got clues. Some of the clues help to eliminate possible suspects. Some of the clues can give you an idea of how the murder was committed in the first place. Now, one of the heuristics that we use very often is to solve a simpler problem. What is a simpler problem? The original problem has 10 persons. 10 persons on a staircase. That looks very difficult. So we'll try a simpler problem, which says that there are only 2 persons. And these 2 persons is the first person here, and then it's the second person here. And then we make a supposition. The first person obviously doesn't know anything about himself, but he can see that the second person is red. So if the first person were to shout out, red, then the second person, if they had colluded before and was told that if the first person said red, then the color of the hat on my head is really red. And then he would say red. And the second person will definitely get it right, yes? So although the original problem required 90% correct, basically what it's trying to say is less than 10% wrong, or not, in terms, percentage is not important. It means at most 1 wrong. So we look at the problem as the first person has to sacrifice himself. It doesn't matter whether it's right or wrong, but he wants to give information to the second person who will definitely get it right. Yes. So the first, if there are only 2 persons, it looks rather simple. That means the first person merely tells the second person what the color of his hat is. Okay, so let's understand the problem. The first person is the one who is allowed to be wrong, because there's no way he will know what is on top of his head. But because he's the first person to speak, what he says will be clues to the others. Isn't it nice? So now, if the first person, there are 2 possibilities, either the second person, and we don't care what the first person is doing. If the first person, the second person either has a red hat or a blue hat. There are 2 possibilities only, this one or this one. If the first person sees, they agree beforehand, the first person sees the second person has a red hat and just says red. And if he sees that the second person has blue hair, he says blue. And that's the rule they agree on. This is the rule when there are two persons. When the second person is red, the first person says red. When the second person is blue, the first person says blue. And surely you will get it correct, yes? That is a simpler problem, really simple problem. But what happens if there are three persons? What happens if there are three persons? Just now, we talked about another, we introduced, we showed another heuristic called systematic listing. If there are three persons, then what are the possibilities? We can have the first person as before, we don't really care. Systematic listing means that, well, there's three persons here, right? So, see, click. Let's see where the color is, color. Sorry, the color is. So we could have that the second person is red. Sorry. Okay, never mind. We could have that the second person is red and the third person is also red. Systematically, second person is red, third person is blue, or we could have blue and we have red, and we have blue and blue. These are the only four possibilities for the second and third persons if the first person is ignored. There are four possibilities, and recall that the first person can only say two things. He can either say red or blue. But there are four things, there are four possibilities. And that is our first quandary, the first thing that blocks us. The first person can say two things, but there are four possibilities. How do we get the message across to these persons on what color the hat on their head is? So let's try. The story, if told this way, would mean that at this point, there's a really big question mark. And just like Poirot, detectives will face sometimes the most puzzling part, and this is where you have to really sit and think very, very hard. How do I get this message across? Either through luck or through thinking a bit harder. Here's a possible rule. When the first person sees red, red, or blue, blue, the first person will say red. When he says red, blue, or blue, red, he will say blue. Now let's see what that means. Okay, those three persons have already discussed beforehand. So the second and third person will say that, you know, if the first guy says red, then we will know that it's either red, red, or blue, blue. So let's say, suppose we have this situation here now. It's red, red. Therefore, the first person said red. Now, this guy heard red. And he sees red. So he heard red. And he sees red. And he knows that when the first person says red, it's either red, red or blue, blue. And he sees red ahead of him. So he knows that he himself is red. You agree? Now the second person. So he shouts red, the first person. The second person heard the first person say red and the second person say red. He heard it, his ears, and he saw nothing in front. When he heard the first person say red, he knows that it's either red, red or blue, blue. When he heard the second person say red, now he himself knows that he's red. And so he says red. So this situation works if the second and third person had red, red. Now let's go through the other cases, okay? In a bit faster fashion. If it were red, blue, then if it were red, blue, that means red on this side and blue that side. Then the first person will say blue. The second person will hear blue and sees blue. So he knows that it's either blue, red or red, blue, but he sees blue in front of him. So he knows that he himself is red. Now the third person will hear blue and he will hear red. When he hears blue, he knows that it's either blue, red or red, blue. And he hears red, so he knows himself is blue. Okay. Now, if you go through the other process, you find that this works indeed very, very well. We discover that we have to divide the possibilities into two groups to be called out as red or blue by the first person. Remember that the first person has only two words to say, either red or blue. And if there are four possibilities, he must divide the four possibilities into two groups. One group called red, one group called blue. And then the participants down the line must be able to figure out in a logical way what is the color of the hat on top of the head. Now we get into something really complicated. What happens if there are four persons? Well, if there were four persons, by systematic listing, we will have, now the first person really doesn't matter, so we only have our second, third, and fourth persons, which form the possibility. So we have red, 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 blue, red, blue, red, blue, red, 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 blue, 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 red, blue, 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 red, and blue, blue, blue. There are 8 possibilities for 4 persons. Okay. So at this point, what do we do? So let's think a little bit, okay? I just need to see your faces at this point. And then you can use the chat to give your point of view. What do we do? Okay, I need to see your faces. I don't see anybody's faces. You can use a chat to tell me if any of you have any idea what strategy to use. Any kids here who want to try? Okay. So, slides here. We use another heuristic called determine suitable subgoals. Looks suddenly 8 is 4 persons, 8 possibilities, very difficult. We discover that we have to divide the possibilities into 2 groups to be called out as red or blue by the first person. How do we divide 8 possibilities into 2 groups? What are 2 possible groupings of numbers? Okay, so just think about numbers. Relax, relax. When you think about numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. What is a natural way of dividing them into 2 groups? Anybody? You can use the chat. Very good. Even odd. Yes, even odd. That's the natural way, right? Now, can we use that to try to solve this problem? Even odd. Okay. Even odd. Even odd. Let's see. Okay. So now, if you look at the red, just concentrate on the red. Over here. How many red do you see? 3. Even or odd? Odd, yes. Just look at the red. Ignore the blue. Now look at the red here. How many reds are there? 2 reds, right? So even number of reds. Here, even. Here, even. Here, odd. Here, odd. Here, odd. And no reds. No reds is even odd. 0 is it even number or odd number? By definition, what's an even number? An even number is a number when divided by 2 gives you remainder 0. So 0 divided by 2 is 0, remainder 0. So 0 is an even number. Oh, look. We have 4 evens and 4 odds. So let's make this rule. If there are even number of reds, the first person will shout red. And if there are odd number of reds, then the first person will shout blue. Okay. Let's see whether this works. So you see odd number of red, the first person will shout blue. If you see an even number of red, he will shout red. Thus, in all the 8 possibilities, this is what the first person would say. Okay. But what's important is, can the second, third, and fourth persons figure out what's on top of their heads? Oh, now this is interesting. Okay, let's try the first one here. Okay, let's try the first one here. So this is the rule. When the even number of reds, first person says red. So he sees an odd number of red, so it says blue, right? Okay, was that the rule I said just now? It could be this way or that way, right? Odd number of red, it says blue. Okay, so now this guy hears, he hears blue, he sees, what does he see ahead of him? So this is the guy in question. Huh? He hears blue, the guy behind him is blue, and he sees 2 red. But when he says blue, remember, there's an odd number of red. He hears that there's an odd number of red, including himself. But he only sees an even number of reds, so he must be red himself to make up the odd number of reds that the first person sees. You got it? Now, this is a very crucial point. Huh? What he hears tells him that there should be an odd number of red. What he sees is only an even number of reds, so he himself must be the red. Okay. Got it? Next. Huh? Eraser. Now, the next guy. This guy here. This is number 3, okay? What did he hear? He heard the first person say blue and the second person say red. And he sees an odd number of reds in front of him. Okay, so now he has to do some calculations. Okay, blue says that there are odd number of reds. He sees an odd number of red in front of him, but he also hears the first person say red. So odd here plus 1 red should be even, right? Odd plus 1 red is even. But the first person said that they are odd number. So what he does is calculating odd plus myself plus 1 red down here is equal to an odd number of reds. He knows that odd plus odd is even, so he has to be red. So he shouts out red. Okay. Razor. Now finally, the last guy. The last guy. What does he hear? He hears blue, red, red. Of course, he sees nothing in front of him. Now, in his situation, he hears red, 1 red. He hears another red, and he is here. So he hears that there are 2 reds behind him, but he heard the first person say there are odd number of reds. 2 reds is even. So he himself must be red. So he shouts red. Okay. You get it? Escape first. Any comments? You can put in the chat. Okay, later you can ask questions. And on you can put reactions as well. Well, that's for 4 persons. But the rule is quite interesting. Because the rule says that when even number of reds, the first person says red. When odd number of red, first person says blue. And finally, if we come back to our original problem, because ultimately we have to solve the original problem, which is red, red, blue, blah, blah, blah. For example, this one here. this original problem. And so we use suitable representations, which I have already tried just now, the method of hearing and the method of seeing. So let's use the same rule for 4 as we use for 10. When you see an even number of red, the first person says red. When an odd number of red, the first person says blue. Okay, so let's count. The first person sees 1, 2, 3, 4, 5 red. That's an odd number of red. So he will say blue. He will say blue. Okay. Now let's see whether this information is good enough for all these guys to guess what is the color of the hat on the head. Okay, now let's try this guy. This guy, he hears blue. So when he hears blue, he knows that there is an odd number of reds. Okay? He doesn't know what he is, but he sees in front of him 1, 2, 3, 4, which is an even number of reds. He ignores the blue. So he knows that the even number of reds in front of him. He knows that the total number of reds is odd. So he must be red, right? Let's go to the next guy. Now this guy, the second guy, he doesn't know what he is. He heard the first guy say blue, which means there's an odd number of reds altogether. He heard the guy before him say red, and he can see that there are 1, 2, 3, an odd number of reds in front of him. So there's an odd number of reds in front of him. Sorry, this guy, right? He sees 4, sorry. So he sees an even number of reds in front of him. He sees an even number of reds in front of him. He hears that the total is odd. He hears that there's 1 red behind him. Even plus 1 is odd, and the total is odd, so he must not be red. So he shouts blue. Okay, so now we move a bit faster. The next guy, he doesn't know what he is. He knows there's 1 red here. He knows there's an odd number of red here. He sees there's an odd number of reds here. Odd plus 1 is even, but the total must be odd, so he must be red. Okay. So let's go on. And now I just try to do it as fast as I can. So next guy, he hears total is odd. He hears that there are 2 reds behind him, which is even. He sees that there are 3 odds in front of him. So to him, odd plus even plus himself, unknown, is odd. So what is he? Odd plus even gives you odd. So he himself cannot contribute to the number of reds. Therefore, he himself is blue. Proceed onwards, and everybody will get the color correct. But that is how we solve this problem of the colored hats. It is, if written as a story, it will take longer than the 30 minutes that I took. It will be a a case of struggle, a case of trying to figure out how to divide into two groups of people. We have to think about the proper representations. We have to solve the simpler problem. But all these things lead us like clues to a final denouement, a solution to a problem. Mathematics is about building up. Mathematics is about mastering certain basic skills, strategies. Mathematics is not about cheating. So I end up with this thing about Picasso. If you know about Picasso, he's a very famous artist. He's so famous, his paintings, and this is his famous quotation. He says that inspiration exists, but it has to find you working. How did I solve this problem? Personally, when I first saw this problem, I had to work hard. And then suddenly I got this inspiration. I will say that I would look at the number of reds only and see whether they're even or odd. That's how I divide into two groups. So inspiration exists, but it has to find you working. Picasso is famous for this kind of ugly painting. Okay, this called modern art. You say, you know, does it look like him? Yeah, big eyes, big nose. Yeah, looks like him. You say, oh, this is a lousy artist, but his paintings sell for millions of dollars. He painted himself in 1907 looking like this. But actually, you may think he's a lousy painter, but in 1896, he painted his mother. Look, beautiful, right? The proper kind of painting. And in 1917, he painted his wife, which is a mixture of the two. He could create new art, but he has to master the basic painting first. Then he can be creative. So maths is like that. You're the basic, you know even and odd numbers, you know how to add them up. But now you must learn the strategies, like heuristics, doing a simpler problem, writing out the things nicely, restating the problem, systematic listing. So that's one story. There are many other problems like this. And the fun, as I said, I would share with you, the fun is putting all the clues together and making small progress until you finally get the solution. Yeah.
Thank you, Thank you, Prof. Tay. And now we'll hand over to Dr. Yap.
Good evening, everyone. So my friend Nguyen, Dr. Tay, just led you through the solving of a rather extensive and extended problem. What I'll do now with you is to make a few comments, and we invite you to ask questions. The question can be about the mathematics itself, and Dr. Tay will address those. And then some of the parents, you may want to ask about the learning of problem solving, the teaching of problem solving. And Nguyen and I can address those. All right. So feel free to populate the chat box with the questions that you have, some burning questions that you might have about how we can help our children become better in mathematical problem solving. The first point I want to make after listening to Dr. Tay is this. So what he led you through is rather extensive. I know some parents are thinking, but I need to get my child to go through a lot of practice problems in order for him to be ready for the exams, for him, for her to be proficient in problem solving. The first point I want to share with you is that generally, there are two things that students can do to build their problem solving muscles. The one Dr. Tay led you through is a bit like what I might call exercising. You are exercising your problem-solving muscles. You are doing something, just one thing really, solving one single puzzle or problem, but it took you half an hour, probably an hour, sometimes over several days, but on one thing. That puzzle, that problem is for you to collect a range of skills, to collect a range of techniques. It's for you to build your problem-solving muscles. I call that the exercising way of becoming better in mathematical problem solving. You do one thing, you don't have to do many things, but you keep on working on it. And you probably realize if you were going along with Dr. Tay, you realize that you were doing quite a few things. You were trying out this heuristic, that heuristic, and when you were stuck and he gave you some hints, you make some progress. You change your mind. You gain some degree of clarity. So this way of becoming better in mathematical problem solving does not involve a lot of problems. Just one. To occupy you for an extended period of time. Half an hour, and I said sometimes several 1 hour periods over a few days. The second strategy might be more familiar to parents, and that's the one where you get your child to practice shorter problems. The kind that is probably commonplace in a school worksheets or the school examination. So that kind I sometimes call rehearsing. Rehearsing for doing the schoolwork. Rehearsing for the examinations they are to take, say the PSLE or the school semestral assessments. So my first point this evening is to remind parents that generally, these are the two main strategies children might go through in order for them to become better at mathematical problem solving. The rehearsing way, which is quite common to many students because many parents and even school teachers use that way to make students better at problem solving. And then a less common way, but equally important, also necessary, is the way Dr. Tay has taken time to illustrate the exercising strategy, as I call them. All right, so that is my first point this evening. Parents, do you have questions that you would like us to give answers to? Some things that you might find your own children struggle with? And for the few teachers amongst you, I recognize your names because you're probably friends or followers on my Facebook. You can also ask questions related to how you can help your own students. And I suppose the answer is not very different whether you're a parent or a teacher. So if you do have questions, please put them in the chat function. Is that right? We're not using Q&A function, right? Yeah. Chat function, right? Chat function. Thanks, Daniel. The second thing I want to mention is this. In problem solving, one of the major skills students need, there are probably 3 to 5 big abilities that students need to have. And one of them is communication. Meaning, when someone presents the problem to them, whether orally or in written form, say in the examinations, whether using English language, in the case of Singapore, we use English, or whether in the form of a visual, when they are younger, pictorial, when they are older, diagrammatic, so whether pictures or diagrams. and sometimes in notations, in symbols. So that is one skill that students need to have, to be able to understand another person, whether it is oral language, when the problem is presented orally through a video, or in written form, like in a storybook that Dr. Tay and colleagues have put up, or in examination papers. And in written form, it can be in English language, but also in visual language, as well as symbolic language. So our students, our children, they must be proficient in those three things, three elements of the mathematical language: English, visual, symbols. Likewise, when they want to present their thoughts, where they want to share to the reader, whether it is you, the parent, or whether it is the examiner or the teacher, our children need to present their mathematical ideas. And how can they do that? Of course, they can use the English language, the written words, if they are doing assignments, or oral language, if they are explaining it to a group of people, their friends in class, or presenting it to the teacher and friends. But sometimes they also supplement their explanation with diagrams, with pictures. And of course, they would also use symbols, as in they write equations, they write expressions, right? So ability to communicate, ability to comprehend and use the different aspects of mathematical language, including English language, visual language, and symbolic language. Other than communication, the other important bits that are needed to be quite good in problem solving would be metacognition, which is clearly demonstrated by Dr. Tay in trying to figure out this rather involved problem, the clarity of mind that we eventually got to. At first, we're a little bit messed up because, you know, the situation is not exactly the most easy one to understand. But as we went through it, we achieved some clarity of thought. And we begin to be aware, oh, this thing, maybe we can do that. And we have some realization and be able to capitalize on it. We begin to monitor our thinking steps. And I know some of you were a little bit confused when we were introduced to the idea that when it is odd, we say red, or when it is even, we say red. And we were a bit confused. Oh, red, is it even or is it odd? And metacognition is the mental process that prevented us from being overwhelmed by those complex things that were happening. So other than communication, metacognition, the ability to be aware of what's happening in our mind, the ability to monitor what's happening in our mind, and the ability to regulate the processes that's happening in our mind. So I have shared with you two big abilities that children need: communication, also metacognition. For communication, the English language, the visual language, pictures or diagrams, and the symbolic language. For metacognition, that awareness, the monitoring, and the regulating of things that's happening in our mind. Let us take a couple of questions that has been posted. Where can I find more of these word problems for my child to exercise the muscle? Yeah, and how should I help the child solve it? I will give an answer and Dr. Tay may add to it. I suppose the books that Dr. Tay and colleagues have put out, you know, the three that Daniel introduced to us at the start, we probably see them again. Those are interesting ways to get students to be engaged with such problems. Yeah, so books like that. Eng Guan, do you have some suggestions for parents to go to get more of this kind of rather involved, long puzzle or long problem?
I suggested this person called Martin Gardner. There's lots and lots of problems. He used to have a column on this kind of problems. Of course, there are some with various kinds of difficulties. And some of these problems actually come from our own discussions. And some of them are extensions of problems already existing. Like, for example, if you think about this problem, I say, oh, okay, 2 hats, right? Good. How about there's three colors? Can you solve the problem with 3 colors? So things like that. So the book Martin Gardner I would strongly suggest, and it is our attempt to increase the number of such books by writing them.
Thanks, Eng Guan. So Dr. Tay has suggested Martin Gardner, Gardner, one of my favorite mathematicians. He has a great collection of interesting problems, interesting puzzles. Of course, books by Dr. Tay and colleagues at the NIE would be another source, those published by World Scientific WS Education. The other part of the question is, how should I help my child solve it? Level 1, you expose your child to it. Just let them read the problem, let them read the storybooks, let them have a go at it. And who knows, some of your children are able to take it from there all by themselves, and that would be great. But I think many of them would probably struggle a little bit, not because of anything, but they are not so familiar with this kind of problems, because, you know, as parents, we tend to give them more of other schools' past year papers rather than extended problems like that. So it's just not familiar, not that they cannot do it, they're just not so familiar with it. Level 2, if they're not so familiar with it, we can do what Dr. Tay demonstrated, meaning we kind of solve the problem a bit with them using a simpler problem. Oh, let's try it with 2 persons. What if there are 3 persons? What if there are 4 persons? And spend 20 to 30 minutes just solving it, basically showing them how you might deal with the case of 3. And then together we might try to figure out the case of 4. So that's a level 1 kind of help, where we are actually suggesting to them the heuristic to be used. Oh, it's too big a problem, never mind, let's do something smaller. And you are more or less modeling what you might do. Okay, let's draw a diagram, let's use colors, let's do this, let's use a triangle to represent the head. Yeah, so that's something else that we can do for those of us who have children who cannot really make a start. Another thing we can do as parents when helping them with problems like that is to set expectation. Reassure them, we're just trying this. I have no idea how to do this myself. Even if you do, you can say, I have no idea how to do this myself. Reassure them that the benefit of all this is in the trying. And maybe we cannot get the solution after half an hour. Probably not. Maybe even after 1 hour. But we will stop. We will give it a go for half an hour today. We'll give it a go for 1 hour. And then we'll put it aside. Maybe a few days later, we might revisit this. So a third suggestion would be set the expectation. Make it less stressful, as in making sure they know that the benefit they are going to get out of this is not getting a final solution, but is in engaging with the processes that's going to unfold as they are solving the problem. So those are but 3 things I would suggest parents might do with their children in solving extensive problem such as that. Another question, my students cannot accept visual approaches when they are trying to solve problem, whether it's using model or using a diagram. And they will do their usual method, I assume, doing equations, doing calculations. Yeah. And they cannot solve the difficult ones. And that's not unexpected. When we encounter a simple problem, like I have 19 cookies, you have 25 cookies, you will jump straight away to writing the expression, the addition expression, and then complete the equation and get the answer, because it's such a simple situation. So for problems that are not difficult, we can go almost immediately to the equation. But when we cannot see what the equation is going to be, or what mathematics we need to use, what calculations we need to do, when we cannot see that, we need heuristics, including using diagrams, isn't it? Okay, so the question is, but when I help them to use visual, they will still revert to their previous method. So that's a second question raised. I think the problem raised by this person, probably a teacher, is that my students are stubbornly sticking to doing calculations, writing down equations, even if they were not successful. And even when I expose them to all kinds of methods, including visuals, they still like to revert to their calculation. So this is really an issue of mindset, belief system. Many of our children may have come from certain background where they begin to develop that mindset, that belief system, that doing mathematics, doing calculation is the most important thing. They accidentally develop the incorrect belief system that doing calculation is paramount in doing mathematics, that calculating is the most important thing. So when they try to solve a problem, they try to get to the most important thing, at least in their own belief system. So the problem raised by this person, a teacher probably, is that of a belief system. We as adults can help cultivate a more healthy mindset about the subject, that mathematics is about thinking. Mathematics is about figuring things out. Do not do things that would contribute to the alternate mindset, that mathematics is quick and fast, that mathematics is doing calculation. Yeah, you will do calculation, but that is actually the pedestrian bit. The important part is the thinking part. Once you have thought things through, the calculation is probably the easiest things to do. And these days with technology, in Singapore, even the upper primary students have a calculating device, a calculator with the calculating bit, to underline the importance of thinking in the problem-solving process, right? So the question is, how do I help students develop, how do I help my children develop a positive belief system, a healthy mindset about the nature of mathematics, which is mathematics is thinking, mathematics is figuring things out. Mathematics is not about quick and fast, it's not all about doing calculation, right? So I suppose that's where parents, as parents, we can play an important role. Ingwan, do you want to chip in anything?
No, you're doing fine.
Anything you want to add in? Do just jump in, yeah?
Yes, yes.
I'm really sorry, but we're out of time. So that was the final question. Thank you, Dr. Yip. Thank you, Prof. Tay. The recording of tonight's workshop will be uploaded onto World Scientific's Facebook and YouTube. The links will be sent to all participants in an email tomorrow. Thank you so much for joining us today. And I'd like to remind our viewers that set 1 of I'm a Math Star is available for purchase on World Scientific's website. You can get to the order page for this set by scanning the QR code on your screen. For limited time only, readers can get 20% off their order by entering the promo code WSEMATH20 at checkout. So this offer will only be valid until 31st July. So thank you everyone for attending. Thank you, Prof. Tay and Dr. Yip. Goodbye and have a good evening.
Good evening. Bye-bye.